So let's go on to this. I'll just share my screen, entire screen. Okay, so what I was trying to say is that so you have something called minimum spanning tree, G, which is undirected graph with positive weights. Sometimes there are algorithms to work with negative weights, but I won't get into this. I'm just going for the simplest case of a graph. So this is also known as simple graph um, with positive weights. Positive weights. What I mean by weights is this. Suppose you have this two nodes, 1 to 2, and this is 10. So basically, this one This one is called this one is called weight. So you will see in some textbooks that G is defined as edge meaning this arrow thing, edge, comma V. V is your vertices. Okay, I'll just give you a formal definition. A formal definition. Um, E is represented by agency matrix. You will come to know the representation of graph in just a while. Of a graph, you have something called agency, and you have something called incidence. I'll just give you a brief thing. You have something called rows and columns. One, two, three. This is one, two, and it keeps on going like that. This is your what you can say. Um, all right. I'll come back to this later. Just keep this at the back of your mind. I'll just make a partition. So edge is this one. Um, Set of edges. Um, and then um, it is represented by um, think you have one, two, three, four. Okay, so while watching the video from MIT, came to know that E is cross product. Wait, I'll show you what I mean by this. Um, it is this thing, the definition, and V is set of vertices. Suppose to explain this here, um, this is supposed to be positive weights. Let's make a partition. Um, it looks horrible. Um, so I'll just make a new slide. Um, so let's draw. This is minimum spanning tree. I'll just talk about prerequisite. Prerequisite. Uh, we are using simple graph, where there are no self loops, such that I'll represent this such that with a vertical bar, such that there are no loops from node to node. This is not allowed. Then um, then you have it's connected. What do you mean by connected is there is a path from the starting vertex such that you can choose your starting vertex, and it's connected path exists from the given starting vertex. um, then you have positive weights or cost of age, or positive weight or cost of an edge. So this is your this is g is a function and it has two parameters. This is an age. Then you have the second parameter is basically vertices. So e is defined. The e is defined as the cost it is. That's why I put absolute value, because whenever you have negative weights, right, it turns into positive one. So yeah, and like then you have v cross v. Suppose example I'm giving you example. Suppose you have v equals to 1 comma 2 comma 3 comma 4. So what I'm going to do is just take this and write down 1 comma 1, 1 comma 2. What I'll do is I'll double this. Then you circle around this and you just do it like this. One is related to this. One goes to two. Sorry, one goes to one. One goes to two. One goes to three. One goes to two. Uh, one goes to four. Sorry. So you go until you get 1 comma 4. Similarly, um, you have 2 comma 1. Now you choose this. I'll just mark this with a yellow marker. Then you go this 1 2 comma 1 2 comma 2, and you continue till you get 2 comma 4. You continue till you get what is called 4 comma 4. 4 comma 4. So I'll zoom out just so you guys can get a bigger picture. I give you the example just you can understand what I mean by the cross product. This is, sorry, not a crosswise, it's called Cartesian product in discrete mathematics. So discrete mathematics. uh, I hope you guys are understanding what I mean by this. And then you have V is the set of vertices or nodes/nodes. uh, Now you have this kind of a precursor knowledge. So let's move on to the next slide. Hmm. So I'll refer to this. Okay, so I forgot to talk about wait a minute, what is going on? Oh no, I think you are listening. Okay, good. So okay, what I mean by minimum spanning tree, let's talk about the formal definition of tree. Mm, so tree, um I forgot actually. I'll come to it later. Anyhow, so I'll just leave a space so that, or I can just Google it up. Later on, I'll do it. I know the definition of spanning tree. It's a graph with no cycles. With no cycles. That is all you need to know. A tree is like what you can say. There is no restriction. Like it can go to this node, then here like this. Wait, I should just Google it up. Formal definition tree. Oh no. In graph theory, I must say. It's an undirected graph that satisfies any following equivalent conditions. G is a connected and acyclic. There are no cycles. It's connected and there are no cycles. So what I'm going to do is I just copy and paste it right here. A text. So A tree is in. Okay, I'll just make it bigger. I think this is enough. A tree is an undirected graph that satisfies any of the following equivalent conditions. So, the formal definition of tree comes here: G with no cycles. I am not sure about the minimum spanning tree. Okay, anyhow, let's forget about it, or else we will get stuck in here. So, let's make a new slide. Okay. Mm, okay, this one from Wikipedia. Let's check this out. A tree sequel. Okay, okay. This makes sense. This is an example, great example of a tree. Um, yeah. So let's explore prims and cruscals. I'll talk about the algorithm and not a usual proof, cause it's easy for humans to understand. So what I'm going to do is do a partition and we will take an example. So this is what you can see. Um, so this is it. So A equals to empty set, and while A does not form a, huh, what does this mean? Okay, let's move on to the implementation part. Hmm, hmm. What I'm going to do is like open another textbook. I'm getting lost. So let's move on to Drive. Hmm, let's open up the another textbook right here. This one is great. Hmm. Um, Wait, I missed something out. It's called dynamic programming, and I think minimum cost spending tree is a part of greedy method. So I'm going to go to page number 216. Um, 216. So yeah, this is it. Let's skip. So you have given. So what they have done is that they took this example. Wait, I can't highlight this example. So what I'm going to do is copy this example. I think I can just use a snipping tool. No, a screen grab. It's used by cybersecurity analysts. So copy, and then you have. Let's use this as a reference. So in prims, you would choose this list one, because you can see 10 is the minimum cost. So you will start with 10, and crucials also will start with 10. But and then like um for this, it will choose whether this one is accurate this. So it will go for this because this one is clearly greater than this. So it will go for 25, and it will find the next minimum cost, which is this 12. So it will go for 12. Continue till you get MST. Continue till you get MST. So yeah, this is technically what you will do by hand, but computer doesn't know the logic. That's why we will use this to actually like explore this one. I'll highlight what we will be going through. So this is it, and it will end till here. So yeah, technically we have to like read this part example. So it will explain how it works here, right here and there. So it will take a lot of power, visualization power. So what I'm going to do is rub this off. So I just zoomed in just so you guys can check it out. Um, so what I'm going to do is just read this part. So I just explained this to you a while ago that the algorithm will start with a tree that includes only a minimum cost. Then the edges are added to this one by one. The next edge, I comma. Okay, so basically, I need to talk to you about the representation of a graph real quick. So you have something called agency and incidence. So you have one, two, three, four, five till n. One, two, three, four, five till n are what you call rows. This is what you call columns. So you will draw the partition and you will fill this up with zeros because um what I'm trying to explain is I think it's the charging is low. So yeah, coming back to it. So this one corresponds to this. This one corresponds to zero, and you continue till you get zero. Uh, yeah, the columns, the nodes are represented like this. The nodes. One, this is one, two, three. Here they are represented as columns and also as rows. So the nodes are represented as rows plus columns. An incidence matrix is your edge. Edge 1, edge 2, edge 3 till you get edge n. And you have node 1, node 2, node 3 till you get n of k. I hope you guys get it. Or sometimes in some textbook they are represented by like this, which is quite easy to understand. So Vn. So suppose I'll take this example. E1, suppose I take it as um, what you call 10. So it differs. It is like edges are um, edges are rows and vertices or nodes are columns. Basically, In programming, we use this instead of this because this is complicated. This is complicated. So, computer understands agency matrix. So, let's move on to the next slide. Um, again, delete. What I am going to do is copy this and like put it right here. So, let's talk about prims. So, what I am going to do is just take a screenshot and paste it here. And then let's use this. Uh, where was I? Right here. I think this is enough to understand. So let's annotate. So let's view it, guys. This one is done. Red one. Then the next age is represented by what you can call. Uh, Suppose this is one, right? You can represent it using this. I in mathematics is represented by row and plus J is your column. So this is what it's saying to be added such that vertex such that I is included in the 3 and J is a vertex not to be included. So I belongs to okay. So what it's trying to say is Vertical bar is again such that um let's see, if I can do it, then I'll just wrap this video up by explaining this Prim's algorithm because it's taking a while. I haven't looked at it. I haven't read it properly. That's why I'm struggling with it a lot. So yeah. So technically we're in the same boat. Let's just do it. Mm, oh, okay. So I'm just reading it in my head, and then I'll tell you the this one my logic behind it, my approach. Um, and your weight is represented by cost of I and J minimum. It has to be minimum. Yes. How do we generalize this? So what is saying is that how do we generalize or abstraction? So we have represented it using this K comma L, where K belongs to graph and L does not belong to J. That's all it's saying. Hope so. Um, we are done. So let's strike this. We don't need this. Let's strike this one out also. How many lines are remaining to be actually like finish this up? To determine this age efficiently, we associate each vertex, say, to a value of j. So to include j, okay, such that now I can write galaxy pen is represented using 28. So I belongs to G, comma J does not belong to G, and near of value near J. So yeah, technically we associate J as an index of near. That's all it's saying. So let's rub this one out. No, I think we need this. This. The value near J is a vertex in a tree such that the value of near is a vertex in the tree such that we are defining this. I'll highlight this. And let's do some partitions. And such that cost of J comma near of J is comma cost J plus 1 near J plus till you get cost of L comma near of L. So we define, so this is done. So we will strike through this. Um, so we find this as 0. So we will highlight this as 0. To reiterate, um, the next edge to include is defined by vertex A such that does not equal to 0. Let's make a new slide because it's getting congested. Um, so what I'm going to do is create a new slide and let's do a infinite canvas. I can do it now. To okay, sorry. I'm still in highlighter mode. To recap, um, from let's take an example, same example to such that um, this is your I, this is your J, so that I belongs to graph or and J does not belong to graph. Then you have near of J is defined as um, is defined as Okay, such that minimum of cost j let's use an eraser j plus 1 cost of j near j. Is that what I was trying to tell you? Oh, I think I am on a right track till you reach cost of L and near of L. So let's talk about the abstraction. K and K belongs to graph and L does not belong to G. Smile, smile. So let's read this part. This part. This is it. To include is the next age to include is defined by the vertex j such that j just does not equal to 0. Um, a second. I am back. Sorry for interruption. Where was I? Um, basically, near of J is initialize 2 0, which represents not graph, not does not belong to graph.
याच्याकडचं काम समजा का पेशींकडचा.
Yeah, in the year of J. I think we should end this session. It's getting lengthier and lengthier. Wait, I'll check. What's the time? Okay, it's already 1 hour approximately, so I should end this. Okay,